Right, so we're gonna change this so the name's correct. So we're gonna use the P2P compute shader, Verlet Cloth Collision P2P, and we do the swapping, and we use particle scratch UAV, particle UAV. Oops. That's giving me some nice errors for some reason. Not entirely sure why that is. Now, like I said, because this is actually this is just handling the particle buffers, we only need to transition these resources. So before we do the swapping, we do the transition resource. It's giving me an error saying identifier. That's bizarre. Oh, my bad. Yeah, I'm using the bloody class name, not the instance name. How stupid. Yep. 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 Resolved. Get rid of this. So we sync the particle buffers and swap. Okay. And that's all we need to do for this, because then once the iterations are done, like I said, this actually isn't constraint iterations. This is self-collision iterations. So yeah, once this is done, we can then read back the data. So I've actually copied some code that I wrote from the above readback for the constraint solve. Just one small note actually. Technically, in position-based dynamics, resolving constraints refers to the actual internal constraints, the edge constraints, the cloth, any other constraints that might be used, but also the soft collisions and the external collisions. All of them projections are typically called resolving constraints. However, my terminology for this relates to that the actual internal constraints are the constraints, and I explicitly call collisions. So technically, when I say resolving constraints, I mean the constraint function that does the internal cloth constraints, and then the collision constraints and the self-collision constraints are actually solved by the separate respective collision operations, functions, whatever. So that's just a reference. We could explicitly sync like the particle buffer again, even though it should have been synced in the last swap of the iteration. So yeah, I just explicitly sync this. We do not need to read back from the hash grid indices buffer, so there's no need to sync that because there's no need to transition the resource. So we just call it for the particle buffer. So we're gonna self-collision compute shader, and then we call unbind shaders. So we're going to unbind all the shaders from the compute shader state, once that stops any incidents occurring where the shaders could still be the buffers could still be modified by some other shader, or yeah. So it's just what we do. So we clear the kind of global bound state, just like you would in OpenGL. You clear the bound state of the buffers. And yeah, and then just in case we have an odd number of iterations, where like if we have 3 iterations, then the actual scratch buffer might be bound to the original particle buffer, and the scratch buffer might be bound to the original non-scratch buffer UAV. So we explicitly rebind them. So the particle buffer reads the particle UAV, the scratch buffer reads the scratch UAV. And then we actually, I mean, technically you don't need to rebind the scratch because we're not going to read from it, but I guess it's just good practice to do so. And then we need to read the updated particle state back to the host and pass it to the component particle array. So basically just doing the reverse of what we did up here, we're doing a readback. So we go device particle buffer to host particle array. So I guess the same thing again, we get a reference, but in this case we get a reference to the particle buffer from the device, we do the whole reinterpret cast of the pointer. This C here we're doing read only because we're reading from it, not writing. So remember the enum here was set to write only, but this is read only obviously. And then the destination is the host particle array, particles here. We get the data, which is obviously the pointer to the first element. Call fmemory memcopy as before, and then we can unlock the buffer. So pretty simple. That's all done. So that's basically all the render operations that we need to do on the render thread. So we can come out the render thread here, end that lambda, and we'll re-add this hash grid indices buffer, which we'll then save release. So at the end of the operation of this call, of this self-collision device call, we're going to deallocate the buffer. Now I don't believe the UAVs need to be deallocated. I might be wrong. Let me check. Yeah, I do need to do that also. How stupid of me. So I'll also say if hash grid indices UAV is valid, then hash grid, so I could spell valid, wouldn't it? Then hash grid indices UAV dot save release. Cool. I just like to align these just out of and that's that. And then they'll be recreated on the next time step, or whenever this function's called again, and passed. Now the resource array here doesn't need to be allocated because, like std vector and in the standard library, tarray and tResource array actually has an allocator internally that handles the allocation and deletion. So when this tarray goes out of scope, when this tResource array goes out of scope, then it will just call a destructor on the elements, on all these temporary cell index list elements will be deleted. Yeah, so that's fine. So that's an initial implementation of the boilerplate on the CPU. Now I need to actually implement the compute shader, and for that I'm going to go back up to the original CPU implementation of the function, which is cloth solver collision P2P. Okay. So how I said that I didn't know if I was going to need any uniforms. I need to pass the particle radius to the GPU. So I'm going to have to go back and implement the parameter struct so I can pass uniforms. That's easy enough. So like I said, I left it in a state that I could easily do it. So we call this macro begin global shader parameter struct, and I'm just going to call it Verlet self collision P2P compute parameters. A bit long, but that's not the actual name that we reference in the compute shader. As you remember from before, we actually call this call this implement global shader parameter struct, where we then map that to a string, which is what we actually reference in the compute shader to reference those constants or uniforms. Constants, uniforms, the same thing. Uniforms is typically OpenGL syntax. OpenGL terminology, and constants is what a constant buffer is what you'd call it in DirectX, but it doesn't matter. Okay, so you use these this macro shader parameter, where you pass the type and the shader parameter. So it's going to be a float, it's going to be particle radius, and just to save save doing the same calculation in each thread, I'm also going to calculate. I'm also going to pass in 2 times particle radius squared. So I'll call this particle radius square 2. So it's like, because it saves doing square roots. Again, like in the CPU implementation, we want to avoid doing square roots as much as possible because they're very expensive. And it's easy to work with square distances and only square root the final distance. So that's that. We have to come up here now in the source file That's the header. Obviously, we have to now in the source file call this implement global shader parameter struct, which we then pass in this name, which we just use this Verlet self collision compute parameters. And we're going to map this to this. I'll just use Verlet as the prefix, I guess, because I probably shouldn't have used it, but I guess I accidentally copied Verlet to Verlet constraint, so I guess I'll just call this Verlet self collision uniform just for consistency, you know. And then that's that. And then also I need to implement this set uniform member function, so I can actually set these uniforms in the render thread before dispatching the compute shader. So we have FLA. I need to change this to be FLA compute parameters, and then I can uncomment this. I need to correct the name. No, that's not right. I need to correct the class name. My bad. Notice the lack of syntax highlighting here from IntelliSense makes it quite hard to read, I guess, but you know. So it's a uniform buffer. Pass the command list. Every call of the global shader takes in the RHI command list as the first parameter reference to it, and then in this case the compute parameter, the constant parameters of the buffer. We get the bound compute shader, which is obviously the compute shader that we've just created, and we set the uniform buffer to this. That looks all good to me. So now we'll go back into the compute shader dispatch, or the actual implementation of the component. And I've already forgot what I called this function again. Oh yeah, solve collision P2P device. Okay. Okay. And then if I just reference the previous one I wrote for the constraint solve, yeah. So I actually need to create an instance of the uniform struct, which we just created and defined in here and implemented here, and then set the values and then pass it using that bind function we just implemented. So I'll just quickly do this. I think I forgot a step actually. I did. Good job I came back to this. I've just realised I actually forgot to bind the particle buffers after the device transfer. I forgot to bind the the particle buffer and the particle scratch buffer and also the hash grid buffer. So I need to do that. Again, I'm sorry that I'm just copying a lot of code here, but this again is stuff that once you've wrote it once, you don't need to write it again really. Just modify it for your use. So once the host to device transfer is done, we then need to bind the buffers so they can be used in the compute shader. So that's what I'm going to be doing here. So I'm going to get the self collision compute shader, call bind particle buffer, pass the RHI command list, and then pass the particle unloaded access view reference. And then the same here, bind the scratch buffer. And then also we're going to do the same again, but we're going to call bind the hash grid indices buffer, pass the RHI command list reference, which, if you don't know, by the way, is from the Lambda RHI command list. It's the only parameter that the Lambda has. And then obviously we get the UAV, which we've passed into the Lambda by reference, which is hash grid indices UAV. Okay, and now we need to create a instance of the constants or the uniform buffer, which we'll just call uniforms, and we have two values here, which we're going to pre-compute. So we have uniforms. Now, if I can just get rid of this, we have uniforms.particle radius, which we can, which actually, I mean, typically you would be storing particle radius per particle, so you can modify particles per like individual radiuses, radii per particle. But in this case, I assume all the particles have the same radius, which simplifies some of the calculations with the constraints. And for now it's fine. So we can just get the global particle radius parameter, which is set by the U property particle radius, and then we'll calculate the 2 squared particle radius, or 2 times squared particle radius as well. So let's see this particle radius. This will be particle radius squared. Oops. Times 2. Perfect. So that's that done, and then finally we need to just bind this into the self-collision compute shader instance. So self-collision compute shader, and then we'll call bind uniform buffer. Where is it? Bind uniform. Huh. Oh, set uniform buffer. Probably should have called that bind, I guess, but oh well. And then we'll pass in the uniforms instance here, which we just created by reference. Cool. Oh, getting an error. Ah, yeah, you need to pass in the command list. How stupid of me. Okay, that's that. Good. Okay, and then obviously down here is where we set the particle thread block count. The thread block count, yeah, and then the dispatch code, the synchronization, the rebinding of the original UAVs, the device readback, and then the cleanup. So that hopefully should be the host code now done, unless I've made another mistake, which I'm sure I'll find out soon enough. Onto the actual GPU implementation of the self-collision. So I go back up to the CPU implementation. Okay, and like I said, because we don't want to create a data race, so we can't actually assign, like in here where we're setting the current position, the current point and the other point positions, both of them. One is the negative direction, one's the positive direction, so they actually move apart in the direction, the original direction of heading, and the inverse direction, so they're projected, so they're apart. But we don't want to project both particles at the same time. We only want to project the current particle that this thread on the GPU belongs to. And then the other particle will also be projected itself in its own thread, because it's reading the same positions from the scratch buffer. That's the whole point of using a scratch buffer. If we modified the position of this particle and then read it back into the same buffer, like in a Gauss-Seidel style solve, well, when it comes time to this particle, the other particle, to evaluate its projection, it wouldn't actually register a collision, because now this other particle is now further away from it, so it wouldn't actually register as it wouldn't pass this if condition of the distance. So that's the whole point of, we have this preview state which we read from for all threads. We then write to a separate buffer, synchronize, and then swap. Read from, write to, synchronize, swap. So it's safe. It eliminates data races at the loss of convergence, because we're not injecting those newly computed values back into the iteration. But in this case, it's impossible to do that effectively in multi-threaded. Like I said, there is other approaches of using graph coloring and stuff, but much more complex and requires more synchronization, which for real time isn't very fun at all. So we're just going to implement the same logic. Like I said, now the hash grid's on the GPU. We have this structured buffer of a cell index list, and we should have cell IDs up to 64 cells, up to 64 particles per cell. The count, which is the total number of these 64 that are actually allocated, and we can loop through just like here. And therefore we don't have to worry about the whole O(n) squared problem of checking every particle against every other particle for self-collisions, which would be extremely slow even on the GPU. So yeah, basically that's what we're going to do. So we get the current thread, we map it into the particle, we read the particle into just a local copy from the scratch buffer from this index, and then we create a projection delta. This is going to be like I said, the total projection, and because each particle may collide with multiple particles, we're going to accumulate this projection delta for every other particle in the cell index that the particle collides with. So of all particles in hash grid cell to form particle pairs, check for intersecting radii, which we've covered already, and then we only apply the current point projection, and yeah, for this thread. Cool. And then we write that back into the particle buffer. So we're gonna loop through. So this is where on the CPU side we get the T array pointer to the hash grid index. Well, in this case we're gonna get the cell index list from this buffer. So So we'll say what do I call it on the CPU? C list. Okay, so C list equals, and we're going to get this. So we need to know what cell particle is, and that's easy because the particle stores its cell index as a member. So we just look up the cell index, which then maps to the offset in this structured buffer. And like I said, there's currently the hash grid has 1,000 cells, so it could be 0 to 999, and yeah, and then we just read the result indices from that, so which are stored in this in this cell index list, which we just all set up on the CPU and to pass to the GPU. So we look at the point cell index. Oh shit, how do I want to get the case right? There we go. Cell index. So now we have this. And so we basically read this. I mean, technically this is like a little bit of a copy. It'd be nice if we could have references here, but it's just nice to bind it to a variable rather than calling this this indirection every time. And now we're going to loop through this list of other cells and compare the distances and check for intersection. So what do I say? I use the index J. I just like to match the indices I use on the CPU to the GPU just for easy debugging. So for int J equals well, J is less than. Now this is where we can use the CList.count. Now, opposed to checking every of those 64 indices to see if that cell actually has 64 particles in it, like it's useful that we store the count. You know, as before, we actually store the where is it? We store the count of particles within the cell. So instead of just checking every one of them, we only check the ones that we know are in there. So yeah. And now we're going to evaluate the collision for both particles. But first of all, we have to check. We have to do an important check, right? Because even though this is the current particle cell index also contains the current particle, and we don't want to evaluate a collision against our cells because that would create like an infinitely small radius and would create like a collision that would never be able to be resolved because we'd be projecting ourselves one way and projecting ourselves the other way. So the simple thing to do is we just check, and this is going to create a bit of branching. Ideally, you want to avoid branching obviously as much as possible on the GPU because you create warp divergence, thread divergence as well. But it's just something I'm going to have to do here. So the easy way to do that is just to say if we'll bind the current particle to a variable just for ease of access. So we'll say we'll get the CList. Actually, I like to call this current point, like on the CPU maybe, and then call this other point. So I might actually use that notation. Current point. Make sure this is current point. Then this is going to be other point, and we're going to get the CList, and we're going to get the internal array, which is the actual cell IDs. And we're going to get it for C. Now remember, this is just indices, so we then have to actually use this indice to look up the actual particle, the Verlet Cloth particle from the particles buffer. And because we are reading from the scratch buffer, we remember to read from the scratch buffer. So this becomes a double dereference. Okay. And then obviously, like I say, we need to check if this other point is the same as myself. Excuse me. And if so, we skip this particle, we continue. So Now actually you could just check the index against the ID of the current point. Like you could just check this index here, but now that we've got it bound to a variable, I'll just access the ID member. So say if other point ID equals current point dot ID, then you could basically just check it against the index of the thread and the index that we just retrieved from here without doing this bind, but it doesn't matter because we're going to use this bound variable anyway, so we can just check the ID. Like I said, the IDs are aligned to the indices of the array, so the IDs match the indices of the host array, the particles from 0 to n, and likewise they match the indices of the buffers, the buffer representation of particles. So we can use the indices and the IDs interchangeably to ID the particles, which is very useful, and it's a kind of key point of this whole project to have the IDs mapping to the indices. It makes it much easier. We don't have to do any kind of like hash map from the particle offset to the actual particle index. So if it's the current ID, then we continue, because we do not want to evaluate ourselves as a self-collision. Okay, and then simply now we're going to get into the square distance. So we can basically just, I might copy the square distance function into the compute shader. So opposed to doing a square root, we're going to do a square distance. So we want to get the distance between two positions, and we want to, rather than square root in the result, we want to just get the square distance. So we're going to have a square dist, and we take in two positions, plot 3. So say A, plot 3, B. And we can actually use a single line, so we'll just return a dot x. Oh no, actually, I mean it doesn't actually matter in this what order you do the subtraction, because we're only returning a scalar, but it doesn't matter. So say a dot x, b dot x minus a dot x, and then we need to square this. So does directx have a function for squaring, just so I can avoid writing it twice? Directx square function. Compute shader. I don't want square root. What's it called? Oh well, you could use power, I guess. It must have a power function, right? Yeah. I can just use power then. Yeah. I got syntax highlight then. What the? That's bizarre. Never got that before. It's interesting. So we want to return this plus plus the y component plus. So yeah, this is basically just getting the vector between the two positions and the square distance of it, which you would then typically square root, which would be equal to a Euclidean distance function, the vector magnitude. But we're not actually doing the square root, we're just keeping it as a square distance for efficiency. So yeah, the z component. And boom, that's it. So that's a square distance function. Let's see if I remember the semicolon, check I've not made any syntax errors. Power 2, power 2, power 2, bz minus az plus, yep, that looks right to me. Okay, so now we can just simply do what we do on the CPU, where we check if the intersection distance is, if the particle distance is less than the particle radius squared times 2. So we can just use dist square equals square dist, and we'll pass in the current point dot position. Remember to use the current position for this. The only reason we use the previous position is to derive the direction, which we'll get to in a minute. other point position. And then if dist square is less than, now we need to actually reference our uniform, which I can't remember what I called it now. Let me check in the header file. Oh yeah, particle radius square. What did I actually call this uniform struct again? Oh yeah, Verlet self collision uniform. So yeah, we can just reference that simply by calling this and then dot and then particle radius square 2. Now typically you would add some small epsilon value, but for now I'm just going to leave it as is. So we're saying if the square distance of these two particles is less than particle radius squared, they must be intersecting, the radii must be intersecting. So we need to resolve their collision discretely. Okay, now we need to know which direction to project them against, and like I said, we're resolving probably an intersection that's already occurred. So hopefully we can use the previous position from the previous time step, and we can use the vector by that position, and we actually just use that vector to calculate the distance, but we can actually use the normalized version of it now to get the direction of heading, and we can then project the particles away from each other along this vector. And the reason we use the previous position vector is because if we use the vector between them from the current state when they're intersecting, if the centers have crossed, we might actually end up projecting them in the wrong direction away from each other, which will cause the cloth to become tangled very quickly. So we project them away their original, like along the inverse direction of heading, so that they are touching but not intersecting. So we can calculate this direction vector and then just normalize it, because obviously it's just a direction. So yeah, so we use a float free. Technically, in like math literature, in terms of papers and PBD papers, this would be the constraint function, and this would technically be classed as the normal, even though it's technically 1D. It's a line segment, but the normal along it lies along the direction between the two particles. So basically, just the subtraction of the particle positions. So we take the other point dot position subtracted from the current point dot position. And remember, what have I just preached? We need to use previous. And then we can actually call normalize directly. So we call the normalize HLSL function, and we have the direction vector to project them along. Now we need to work out the actual intersection distance. So to do that, we take the particle radius times 2, particle radius squared times 2, and we subtract the intersection distance. So their actual distance from each other, we subtract from that. And then we know the actual delta that we need to then push them back so that they're touching. And again, you probably should add a small epsilon value to account for rounding error, but for now I'm just going to do it as is. So the intersection distance we will actually square root, because we do actually want to get the non-square distance to project them. If we end up projecting them along the square distance, they're going to be like shooting off into a massive distance. So that's we can just use the square root function, and this is the only square root we need to do now. And we take the uniform particle radius squared, which we just got from up here, particle radius squared times 2, and we subtract this. We subtract the distance. Hang on. Yeah, the distance squared that we just start up here. So subtract the distance squared. So we have this radius minus some intersection distance, and then once we know that, we can use that to project them out. Okay, there we go, we're back on. Don't know what happened there. So yeah, do this, get the square root of this. Now that's the intersection distance we need to resolve. and then we project the current position on the negative direction, which if you think about, we have this particle, the current particle, and the other particle. So the vector pointing, the direction vector is pointing to the other particle. So we project the current particle away on the inverse direction, and the other particle goes along the positive direction, which creates this separated projection, which is what we're implementing. So like I say, we only want to store the delta of the current particle on the GPU version. So like I say, we resolve both particles on the CPU, but for the GPU, because of the parallelism and the data races and the Jacobi implementation that we're doing, we're only going to actually resolve the current particle. So the other particle will be resolved later on. And because we need to account for multiple collisions, we're not actually going to write this directly into the buffer. We're going to store this in this projection delta, which will then accumulate the projections for every particle. So I've just realised I'm writing this outside the I'm writing this outside the cell loop. Oops. So this is where we're so we'll say projection delta plus equals actually, yeah, it'd be minus equals the times. So then it'd be interdist times 0.5. Now the reason we do it by 0.5 is because we want to distribute it. Typically it's distributed based on the mass, and we're assuming that all particles have a mass of 1, so therefore the inverse mass would be 0.5, and that's what we use. So it's kind of like Newton's third law, like, you know, we need to split it in half for two particles. One gets projected one way, one gets projected the other way, you know. It's like equal and opposite. Basic Newtonian physics. So yeah, now we store this. Now you might think, oh well, this will be a problem when the other particle gets evaluated, but you've got to think the other particle will actually be on the other side. So a negative, it will be negative, which will then turn positive. So this will actually amount to a positive direction projection for the other particle when it's evaluated in its thread. So that's one thing to note. Okay, so once we've looped through all the hash cell particles and determined if there's collisions or not, and if there is collisions, we've stored deltas. Then we can finally, like up to now, we've been reading from the particle scratch buffer when we've been accessing particles, the current particle and the other particle that we're colliding against here. So now we're gonna write to the current particle's position in the current buffer, so not the scratch buffer. Now, because we have to account for every other collision, we don't want to just there might be multiple collisions. We don't want to just add them all as is. We typically divide them by the number of particles that they've collided against. So what we'll probably do is we create a variable that will count the number of particles that we've collided against. So we'll just say like we'll say int collided count, and then we'll use this to average against. So every time there's a collision, we'll just increment collided count by 1. And then when we apply the projection delta to the particle position, so we're gonna get the particle buffer. Oops, not the scratch buffer, the particle buffer for the current particle, which we get from the thread index, obviously. And then we're going to get the position, and we're gonna add this delta to it. So plus equals projection delta, and then we're going to average by the number of collisions that have occurred. So now I'll just do this and then I'll cover something else. So actually we need to, I don't want to divide by 0, so we only apply this if collided count is more than 1. So if if collide count sorry, collide count. Does HLS allow single line if statements? I think it does, doesn't it? I'm not sure. Just to be safe, I'll put it in a bracketed if statement. Oops. Particle buffer index position plus equals projection delta, and then we'll have to cast this in just to be explicit. Okay. And now we have those total projections to the particle. We've evaluated both particles, we've applied the delta to the current particle, and because obviously that might be multiple collisions that have occurred between that particle and other particles in the same cell index, we divide that total delta by this. Now you can this is technically a form of under relaxation, so you can actually have a coefficient that you would then control the rate of under versus over relaxation, which is what I've done on the constraint solve. This is covered in the position-based dynamics paper, the original one. So like if it's a value from 0 to 1, it's technically under relaxation, and if it's a value of 1 to 2, it's over relaxation. In this case it doesn't matter, because we don't want any use over relaxation or under relaxation, because it would mean either under resolved or over resolved. So it makes sense for the constraint solve, because over relaxation can actually help speed up the convergence. But for this case, it's probably better that we just leave it at 1. So that just amounts to just having the average times 1, which means we can get rid of the coefficient. So yeah, again, branching, checking if it's actually collided, but you know, it's not too bad, I guess. There's not a bunch of if-else statements. So one thing that we can do for efficiency is we can actually explicitly tell the compiler to branch. In the constraint solve, for example, we were looking at constraints, and we were saying if the current particle is this particle. Sorry, we were looking and checking if the current particle was the A or B particle of the constraint, so we could know which projection delta to add to it. But in this case, we don't need to do that, because we know that we reference this current particle. So therefore, that's the particle that we can actually modify, because we're not looking at some constraint, like some external constraint particle indices. But we can actually use this to tell the compiler to actually branch explicitly. We don't need to do that here, because there's no if-else statement. But we can use this unroll parameter, which tells because we know that we have a fixed number of indices here, cell indices, we can just unroll this, and we know maximum of 64 particles. So per thread will only unroll to another, to 64 of these iterations. And while that sounds like a lot, it's probably faster to unroll it than evaluate the loop on each call. So yeah, the compiler will try and unroll this loop now over all the other particles in the same cell as the current particle, and hopefully that will create a bit of a speed up on the execution. Again, stuff like performance optimizations in compute shaders is much harder to debug in compute than it would be in, say, CUDA or OpenCL, where there's tools that you can use to access the GPU for debugging as much as you would with the CPU. But that's just compute shaders, So just checking if there's anything I've missed. So if collisions have occurred, apply projection delta to satisfy, to resolve self-collision scaled by average, scaled by count. Cool. Right, so yeah, this is the fun part now. or the stressful part, where we can actually just build the code and look for all the compiler errors. Because there's a lot of new info in, like a lot of new code in the headers. The Unreal build tool will run again and regenerate the headers. Because any of the classes, like the component class that uses the U class specifier to enable reflection for these properties, will mean that it has to reparse that and create this, basically macro and evaluate all the macros on it, like this generated body macro. Okay, nice. So we got some nice errors here. So F-cloth constraint cal compute shader cannot access primary Lambda declared. Right, where's this? That shouldn't be calling constraint calc at all. So I'm not sure on this. Not sure what's going on. Not sure. Particle buffer. Right, okay. That's wrong. I should have put this here, the actual correct shader name. That should fix that, I think. Hash grid indices buffer is not a member of FLA constraint calc shader. Wait, where's that? Okay, that should fix that. A legal member designator and offset of. Where's this? I don't know if that might fix that. Okay, source redefinition. Yeah, okay. Because I use the source pointer here for the particle, can't redefine it as a different type, so we'll call this source C dash C, and then in the mem copy. No, I've just realised in the actual hash grid here I haven't actually done a mem copy. I just did the unlock structure buffer, oops. So I'll have to actually do the copy from this. Okay, good job I got an error there, otherwise I wouldn't have saw that I missed the mem copy. Function FLO constraint calc compute shader already has a body. Okay, yeah, you can see that I've left. This is the problem with copying code from previous code that you've wrote. If you forget to change the class names in the function implementations, then you're going to get fun errors. Let's try and rebuild that, see if that resolves anything. Okay, more compiler errors. FLO constraint calc shader. How stupid am I to miss that? Okay, so that built with no more compiler errors now, which is great. That was actually surprisingly very little errors. It was not like that the first time I wrote this code. It was like the first time I did the compute implementation for the Verlet integration. Took a while to resolve this. Now that's just the compiler errors. The fun stuff is the actual runtime errors that we have to actually debug. So one thing that's important to note with compute shaders is that if we go into the Unreal project file, the plugin is based inside the project in the plugins folder. Make sure the plugin is set to loading phase. Actually, I can't remember if the loading phase is where it's set here, or there's somewhere that you set it to load. Maybe it's on the builds. Yes, let me check. I'm forgetting somewhere where you actually you set it to run for the plugin to compile as the engine launches, because it has to compile the global shader. And that's where the actual HLSL compiler will be called to compile the compute shader. And then this is, you actually see errors show up there. You actually have to go into your engine source code. Program files, epic, take 6. I can't remember where it is. I think it's in config. Somewhere in here. Might be. It's not console variable. Actually, it might be console variables. Let me check. Yeah. Okay. So shader development mode needs to be set to 1, and shader compiler emit warnings and load needs to be set to 1. Otherwise, you won't get HSL compiler errors, which you need to debug where you've gone wrong in the compute shader. So now we should be able to just clear this. We'll launch the engine. Oh, very nervous. Be very surprised if I didn't get HSL compiler warnings. Okay, there we go. Yeah. Okay, so this is the good thing about enabling those console variables, makes you get compiler warnings, so compiler errors. So undefined identifier C. Let me see where. Let me see. Pardon the pun. So it's line 131, character 69. One of my favorite numbers. Yeah, C. It's J I should be using. Okay, so then we can save this and retry compilation, which is great. It means we don't have to relaunch the engine. Okay, this is saying, yeah, okay, invalid subscript. This is 137. Yep, pref position, save, retry compilation. Okay, 13708. Undeclared identifier current point. Oh yeah, it should be current point of the C being lowercase. Retry. Okay, 14755. It says undeclared identifier collide count. Right, collided count. Duh. And then 147. Habitation. Incorrect number of arguments to numeric type. I'll just retry that, see if I get. Okay, so that seems to be fixed. Oh, okay. Found unbound parameters being used in shader type F. Okay. Parameter HG cell indices is not bound. What parameter is that? Okay, interesting. So that's not good. So for some reason the buff is not bound into the shader. Let me check that. I'm actually going to close the engine to stop it from launching, so I can try and debug where that's going wrong. So if we look in the compute, so we should have bind hash grid indices. We pass in the UAV. Get the shader. Get the bound. That looks correct to me. The global shader implementation. We have the buffer and we set the UAV. So it must be in terms of passing. So we have this. We have this. This HG buffer. So let's have a mistake of here. Hash grid indices buffer. Great buffer. Okay, this is going to be fun to debug. Because I can't see the error now. I've correctly passed the right structured buffer reference to the UAV. I've then called bind particle buffer, bind scratch buffer, and then bind the. I hope it's not to do with the fact that I'm passing as a reference to the lambda. I don't think it is, because if the lambda can access it for a reference, it shouldn't be a problem. I've never actually had this error before, and this is the first time I've tried using the buffers directly as local variables rather than putting them in as components as members in the component class. So I'm thinking that could be it. But no, the render thread should be able to access external data. I mean, it's been explicitly passed to it, so I can't see why that would be the issue. Let me just go over everything again. So get the data from the source, buffer, hash grid indices buffer, we write it, give a mem copy. Ah, right, okay. This mem copy, I forgot to change the corrected. When I re-change the source and destination mem copy, I forgot to change this to C. I'm not sure actually that is the error, that's something else that I've just discovered. Try again. Be great if that fixes it. We'll see. I don't actually have the symbol libraries for UE4 C at the minute installed, so the debug symbols, they're like 30 gigabytes to download, so that's fun. Okay, well that fixed the problem, so great. Okay, now I'm going to recreate the component from scratch. So I'll create the cloth component. I'll just use this self-collision test geometry here. Let's move it up a bit. We'll build the cloth state, and we'll put a material on it with backface rendering on. Okay, so just check everything works as is without self-collisions on. Yay. Okay. Now the big moment, we turn self-collisions on. Oops. And we hit simulate. Ah, right, okay. Fun times ahead. So we have an exception being thrown. It's reading a null pointer by the looks of it, so that's fun. So we'll just stop this. So and we have the temp index array passed to the render thread, to the lambda on the render thread. So that shouldn't be the issue. We should be able to retrieve the pointer fine. Check that the buffer size is correct. So cell index list. That is the struct that the buffer contains. So that's correct. Times cell count. So that should be 1,000 times whatever the size of this is. And like I said, that 64 indices is statically allocated to that. So there's no need to it's not like the size is going to vary based on how many indices is set. The 64 set, only 30 of them might actually be set. The rest might be set to the default -1. But regardless, they're stored. So the size is the same. So that's not the problem. I don't think this is the problem, because this is just a normal get data. It returns returns a cell index list pointer to the beginning of the array, as we know. Then this is getting a void pointer to the destination, which is the hash grid indices buffer, which is up here and also passed to the render thread. So that, I don't see a problem with that, and that gets explicitly cast to this cell index list pointer by a reinterpret cast. Okay. I really hope this is not to do with storing them as local variables and not just putting them in class members. I might just put them in class members, I mean, I could put them in class members, and then if that doesn't work, then it's obviously another issue. I feel like I'm giving in then, because like the whole reason I wanted to just have these just as local variables is because I've already got a shitload of hang on, where's the header file? I've already got a shitload of RHI references and the structure buffer and UAV RHI references, but I guess it's fine. Maybe I'll just do that. So it's pretty simple, really. We can just move this into the header. So we'll have the hash grid indices buffer, and then the access view HIRF for the UAV. Get rid of the identifier. Oops, daisy. I can get rid of these because they're now passed by this pointer, obviously. And then I'll do the same for the index. For the actual temp T resource array, that can also be a member now. So we'll call this like device state. We'll call this T resource array, style index list. This is the. See, I call this device data, but it's not actually device data. This isn't actually the data that goes on the device. This is just the formatting that defines the memory layout that goes onto the device, but whatever. As you can see, that the variable names don't match well here, but it doesn't matter for now. So that means I don't need to. I can just call this now. Just this defaulted call, and then we'll fill it out. Probably getting this because the header file needs to be regenerated for the build tool, so that should be fine. That means I can now get rid of the reference in the Lambda here because it's now passed through this pointer of obviously of the class of the component class. And we'll see. Okay. Okay, right, the cell index list is undeclared. That's because the header doesn't have a. This doesn't include the. I need to implement this. I don't want to include the hash grid header in here because it will create a circular dependency. So, hang on, does the hash grid include this component? Oh no, it doesn't actually. Well, I could include it, or I could just implement this in the component header. It would make more sense, I guess. Yeah, this is also a device as well. And then I need to forward declare it because it's obviously declared in the class. I like actually putting the definition underneath, which is why I like to forward declare it at the top, and put the implementation underneath in the header, just to keep the header tidy. Although this header is a bit of a mess, and the definitions probably should be in a source file technically, but actually no, I mean, not the definitions, the declarations, but it probably would be nice if they were in their own header, but it's fine to just forward declare them and put the declaration underneath. The only actual definition is just the constructor, which is just implicitly inline anyway, so that's fine. Okay. Hopefully that should have fixed that. Let me check I've just not left anything in hash grid by accident. Okay, nope, let's go. It's getting light outside now. 4 o'clock in the morning. Okay, great. So that's resolved the compiler errors. We'll see if that nasty memory exception shows up again, and if it was related to the references passed in the Lambda. We shall see, and if it was, then I've just moved those local variables to member variables for no good reason, but you know, I suppose like the rest of the RHI buffers and UAVs are member variables, so it doesn't matter so much. I just thought it would be nicer to have them to be local, but yeah, it doesn't matter. Who cares? If it solves this issue, it's easier than trying to deal with the references past the Lambda, because you know, trying to figure out what's going on in the render thread is going to be much more tricky than just moving those variables to the class as members, you know. Okay, so build the class state again. Right, okay. See that this is a different exception, so that's interesting. This is bind particle buffer error, so that's interesting. See, this is where it gets tricky, because this exception gives absolutely no information about why it was thrown. Like, at least the other exception had it was written from a null memory address, like a 0 memory address, but this is just triggering an exception on the bind particle buffer, but for no apparent reason. So we have actually got past this mem copy now, which means it must have been to do with the reference past the Lambda. And you can see, if you look at the source pointer, you can see all those negative ones of those default initialized cell indices particles, particle cell indices, whatever. So then there's obviously an issue in the bind particle. Maybe it's just an implementation error in the bind particle implementation, which would be bizarre because I copied this directly from the constraint. It looks correct to me. Scratch buffer looks correct as well, directly. Oh man. Oh man, oh man, oh man. Just check that it's actually called particle buffer correctly. Particle buffer, particle scratch buffer. Ah, see, the nice green underline issues are showing up again. It should tell me that I've not implemented these definitions, even though I have. Oh, until I sent, what a joy. To be fair, it's pretty good for the rest of the code base. It just gets confused by these compute shaders, which I can't blame it for, to be honest, because it is a confusing mess. Oh, this is going to take a while to debug. I can't actually figure out what the issue is directly. It's probably something really stupid, as usual, but you know, nonetheless, it's an issue that we need to resolve. So we've got the transition resources here, which should be setting it to compute to compute. That's good. This is when I'll look at code that I've read before, trying to figure out what I missed. Just gonna clean up the comments a bit. Well, I'm going to pause this for now while I debug this because it's pointless just me looking at the screen, and you know, I'll resume when I've found the error, hopefully, if I ever find it. I guess one thing we can do for sure, which would be good to rule out, is to disable any other compute operations running. So anything that might, because for example, the cloth constraints device code is also using the particle UAV, and we could check for a case where it's not correctly unbound the the particle buffer, which is something I mentioned before about correctly making sure we unbind buffers. So a good way to just check all this. This is the only other code we have running on the device at the minute, so we can just we're just forced to use single-threaded constraint solve for now while we debug this. Oops. And we'll see if the error still occurs, and then if it does, we know. Sorry, if it doesn't, then we know that it's to do with of our cloth constraints, which has been called before in terms of the time step. It's to do with that not correctly unbinding the particle buffer. So always a fun new challenge in the land of debugging. Ain't that the truth? Okay. So make sure simulate's turned off, and we'll build the cloth state, and then hit simulate. Ah, okay, it still happens. So it's not to do with the other compute shader. That's what we've learned. Okay, back into the wilderness of debugging we go. While I'm on, one thing I forgot to mention is that at the end of the compute at the end of the render thread Lambda, we should always call flush rendering commands, because typically, obviously, the render thread is the game thread is hang on, the render thread is ahead of the game thread. Sorry, okay. So, oh no, sorry, I said it wrong again. Yeah, the game thread is ahead of the render thread, and we need, because the render thread is defining state in the game thread, we need to flush the rendering commands so it actually to sync it with the game thread, basically. So we're basically saying flush render commands, so we evaluate the rendering commands now, opposed to rendering them at some time afterwards, and now it's synchronized with the game thread. So that's important. If you don't do that, you'll start seeing jittering, because it'll be trying to evaluate data from the previous frame or the previous tick. So that's definitely one thing to remember to add. And this can just be added as a separate call at the end of this. Actually, you don't need these safe releases anymore, although we need to. By the way, IntelliSense for some reason tells me that function doesn't exist, even though it does. Again, just ignore it. That reminds me that these now need to be put in the compute setup. These, because this is a function that's called to set up the member component, the component member UAVs. So this can go here now. And just as a complete utter debug, we can comment out every single call on the substep. Obviously, all the build state stuff seems to be fine, so we can leave that commented, which is the build cloth state function, which actually calls the compute setup and gets all the static mesh data and puts it into a procedural mesh. Sorry, and it actually doesn't do that. It gets the static mesh data and creates the particles from it, per vertex. And we can just literally call substep solve and call this soft collision function with the compute shaders being set up. I mean, the compute buffers being set up in the compute setup function. And we can hopefully try and narrow down the margin of error more to find where the actual error lies, the debug error lies. We shall launch this. Okay, so this is what I mean. It builds fine. The build cloth state's fine. So that means all the compute buffers are set up fine. See that we have some output, shows the particle count, the constraint count. But then when we hit simulate, okay, so it's still the issue. Okay, now this is actually a separate issue, which is interesting. So it's saying RHI create structured buffer. It's giving me an error. So it's interesting. So this was obviously one of the buffers that we moved. I mean, this is the buffer that we moved to the component. So technically, this stuff could be actually no. This stuff shouldn't be done in the compute setup because compute setup is only called once. When build cloth state is called, this obviously needs to be done per frame to update the hash grid, the device hash grid representation based on the current CPU hash grid. So this needs to stay on in this function. But I'm getting an error from creating the structured buffer. So that could be any number of things again. Could be to do with this resource array not being set up correctly. Temp index array. Create the resource info, and we pass this into the RHI create structure buffer call. Now this hash grid indices buffer is RHI structure buffer ref, which is the same, exact same as how the computer setup creates its structure buffers. Well, actually, yeah, we actually can create. We can create. That's probably maybe the issue. We should create it once, but then we update it per frame or per substep. So, but then for this, we're going to need. Yeah. So we'll move this initialization code of the temp index array and the create info into the compute setup function, which, like I say, is called when build cloth state is called. So, for example, it just particle constraints, and then yeah. So this. And then we'll move these here. So this is the structure buffer creation. This is the UAV creation. So like they only actually have to be created once. So like previously they were getting created every step, which isn't good. And now because we actually have to have this info to pass to the hash grid indices RHI create structure buffer, we do the defaulting of the array. Also, that's another point. It was adding 1,000. That's probably what was behind. Yeah. So it was adding 1,000 cells to this array every step, whereas it should be only adding it once and then updating them. Otherwise, I'd have to delete this array and reallocate it. So yeah, completely my bad. I missed that out. So yeah, this only gets defaulted once to create those 1,000 or however many cells, and then obviously we're going to fill it with the updated hash grid state in the function below that we did implement. So then yeah, so we do the hash grid, and then we're going to loop through that index array. That we're then going to fill with the hash grid cell indices, and then that's going to be mem copied onto the GPU into the structure buffer, updated per frame or per call. Okay, we'll try and recompile that. Rebuild, should I say? Let's see. I've been at this for 5 hours now. No, 4 hours. Okay. So build cloth state works fine. And simulate works fine. Hey, so that fixed the issue. So it was to do with the fact that I was allocating like n number of new cells into the hash grid index array on the CPU, and then trying to pass that to the GPU into a fixed size of the current cell count. So so yeah, the fact is you make your structured buffer and your UAVs and the temp resource arrays that fill them once, and then you update them dynamically. That was obviously the mistake I made. So me trying to do that all locally inside one function, which gets called multiple times, actually once per step, was the problem. Whereas, like, I should have just done what I did before and had the clear separation of the compute setup, where we actually create and initialize the structured buffer and the UAVs and the temp resource arrays. Like, for example, we do for the particle constraints, the constraints of the particles. In these cases, we actually just mem copy the initial particle data and then update it dynamically. Technically, we don't need to do that initial mem copy because we're going to pass them explicitly in the compute shader anyway when we read from the host to the device. But yeah, like I say, in this case, we actually do a conversion from T array to T resource array. But anyway, because the temp hash grid index array is directly declared as a temp resource array or T resource array, we don't need to do that conversion like casting. Saves a copy. So yeah, and then within the call, we update the indices based on the hash grid in the CPU, and then we call the actual compute code to bind and dispatch. So now we're gonna go back and uncomment this, and we'll see how we get on. I've changed a lot on this commit. Probably should have split this into a couple of commits, but oh well, should be alright. One sec, I'll just pause this. Okay, so once again, we'll build class state and we'll hit simulate. Hey, it's simulating. Huh, and it actually seems to work. Although I can't tell if the self-collision code is working. Right, okay, so I called reset. And we got a breakpoint triggered, which I think might be a related error. So you notice that I called reset to initial state, which actually recalls compute setup because it's resetting the cloth to the original state. And I think the error there is because I didn't delete. Oops, I didn't delete the previous buffer that I allocated. So the resource array itself is fine because that gets deallocated. Yeah. So this is I need to check if it's been allocated already. That's what I mean. It's not fine. So yeah. So when I do the add defaulted, I need to actually check if it's been if the default cell count's been added. I mean, technically this means the cell count can't change because if the cell count changes, then it's going to be a fixed cell count. So I probably should check if it's allocated and then delete it and then recreate the temp array. To be honest, so I'll say if temp index array none, so it's not 0, then I can reset the array. So I think it's reset. Oh, maybe I can reset. Yeah. Shake that done anywhere else. Because cell count is a member like that's a U property that could be changed dynamically in the editor, so the user can change the cell count to adjust the hash grid for the needs based on the cloth that they're using. I don't want that cell count to be allocated and then used throughout. So because the temp index array has to adjust that cell size, it's easy just to reset it and then reallocate it based on the current cell count that's fetched from this member, which is here, cell count. So yeah, so if it's allocated, then we reset it, and then we can do the add default again and create the temp info, which we're then going to use to get rid of this ugly code, which we can then pass to the RHI create structure buffer temp info, yeah, the temp hash grid info. So I hope that's fixed that now. We don't have to worry about the actual members themselves being recreated, because they're updated based on these calls anyway. And then obviously when we actually update the temp hash grid down here, we're referencing cell count directly. We're referencing cell count directly again on the loop, on the for loop, so that should be fine. It's not, it should be. Oops, I just rebuilt this by accident. Okay, let's try this. Okay. Build the cloth state. Simulate. Reset to initial state. Okay, so it still gives me an error, so there must be something I've missed. Oh, hang on. First of all, it should be if it exists, not if it doesn't exist. I think I'll just take a breather actually, and then I'll come back and check if that fix helped solve the problem. Right, let's see if removing the exclamation mark fixed it. Oh god. Excuse me. Okay. So we lost that, simulate, and then reset. Hey, so that did fix it. Okay. So yeah, now that it's not been defaulted every time this function's called per step. If it exists, we reset it and then we redefault it again. Great, so I'm going to leave this here, and then I'm going to come back tomorrow and debug the actual self collision to check this is working actually. To check the computer data is actually working, which I think it is. It's just that because it's set to 4 self collision iterations from when we're using Gauss-Seidel on the CPU, the convergence is so low that we're not seeing much difference, but we'll debug that in a bit. I need to sleep first for a bit, which will probably be challenging.